So as we mentioned at the end of the last video, the exponential functions all have inverses because they pass the horizontal line test. So the inverse of these functions, these are called logarithmic functions. So for any positive number b that is not equal to 1, the logarithm with base b is defined to be the inverse of the exponential function b to the x. We can encode this in one of two ways. It's equivalent to say either log base b of x is equal to y, if and only if b to the y is equal to x, or to express this as function composition, the function b to the x composed with log base b of x, those composed to x, and log base b of x composed with the function b to the x, that is also the function which just outputs x. So because this function is defined to be the inverse of the exponential, we know that its domain is the range of the exponential. That is, all numbers larger than 0. The range of the logarithm is the domain of the exponential function, which is all real numbers. So the logarithm is always a continuous function. When the base b is a number that is larger than 1, the logarithmic function grows without bound, albeit very slowly. So as x gets larger, the logarithm with base b also gets larger. And as x approaches 0 from the right, log base b becomes very large and negative. For a base between 0 and 1, this behavior, just like with the exponential, is flipped. So similar to the exponential, there are some basic properties for the logarithm. The first one is log base b of 1 is equal to 0. This is because the answer to the question, to what power do we raise b to get 1, the answer is 0. The next property has to do with multiplication inside the logarithm. So if you take two numbers together that are both positive, you multiply them, put them inside the logarithm. That's the same thing as computing the logarithm of each of those separately, then adding them together. Unsurprisingly, since the logarithm turns multiplication inside to addition outside, it turns division inside, which is the opposite operation to multiplication, into subtraction on the outside, which is the opposite operation to addition. The next property is actually a special case of number 1, but it's very handy. If you take your favorite positive number and an exponent, r, log base b of x to the rth power is r log b of x. This is simply an iterated application of the first one. For example, log base b of x squared by rule number 1 is log b of x plus log b of x. Oh, that's 2 log b of x. The next property is called change of base. If you have one base a and another base b, and you don't like working in base a, you can change to working in base b by simply taking log base b of x divided by log base b of a. If you have ever looked at a calculator, it likely has exactly two functions on it that you might recognize. One of them is ln, which we'll talk about later, and the other one simply says log. Log generically stands for log with base 10. So if you want to use a computer or a calculator to compute a logarithm, more often than not, you'll need to use the change of base formula. Say if you wanted to compute log base 2 of 3, you would need to compute log base 10 of 2 divided by log base 10 of 3. So for b larger than 1, this is normally the case that we'll really care about for logarithms in this class. If we want to know what the graph of log base b of x is, we remember that because we know how to graph the exponential function, we simply take that and flip it over the line y equals x to get the graph of log base b of x. So if we start with the graph of b to the x and the line y equals x, since b is larger than 1, we know that our graph goes this way. To get the logarithm, we simply take this blue graph here, flip it across the green line, and we end up with its mirror image, log base b of x. Flipping across the line y equals x simply interchanges the coordinates of any point. So we always have the marked point 0, 1 on the exponential function. Flipping it across the line y equals x interchanges our coordinates. So we go from 0, 1 to 1, 0. So if we want to actually compute a logarithm, the only way to really do it is to phrase our answer in terms of an exponential. So if I wanted to compute log base 3 of 81, I could recognize that 81 is 9 squared. 9 is 3 squared. If I take 3 squared and square it, we know that's 3 to the 4th. That gives us 81. Once I've expressed 81 as a power of 3, I get for free that the answer is 4. This is because log base 3 of 81 asks the question, to what power do I raise 3 to get 81? Well, that's 4, so we're done. If I want to compute, say, log base 4 of 2 plus log base 4 of 32, then I can think about using the logarithm rules to combine these two logarithms. Since addition outside the logarithms translates into multiplication inside, log base 4 of 2 plus log base 4 of 32 is equal to log base 4 of 64. Since I know that 64 is 16 times 4, and 16 is 4 squared, that tells me that I can express 64 as 4 cubed. So my answer here is simply 3. For this one, if I want to compute log 2 of 80 minus log 2 of 5, I can combine this as log base 2 of 80 divided by 5. Since 80 divided by 5 is 16, and 16 is 2 to the 4th, log base 2 of 80 minus log base 2 of 5 is simply 4. We can also solve equations involving exponentials now that we know logarithms. We can recognize that 2 to the 2x power is the same thing as 2 to the x squared. So we can think about this like a polynomial equation of degree 2. We can rewrite and factor. Once we've factored this, we have two equations, 2 to the x equals 2 or 2 to the x equals 1. To solve for x, we can apply log base 2 to both sides. Since we can compute all of these logarithms, we have our answer. Either x is equal to 1 or x is equal to 0. We can also solve equations involving logarithms. However, sometimes there's something to watch out for. So first, we can combine the logarithms on the left-hand side. Once we've combined the logarithms together, we can apply the exponential function 2 to the x to both sides. Since the exponential and the logarithm are inverses, the right-hand side simply becomes x times x minus 1. Since 2 to the 0 is equal to 1, we can move the 1 to the other side, and this is equivalent to solving the equation x squared minus x minus 1 equals 0. We can use the quadratic formula to get our solutions. So when we use the quadratic formula, we get two solutions. However, we have to be careful here. We remember that the logarithm is only defined for positive input values. Because 1 minus the square root of 5 over 2 is negative, this gives us what's called an extraneous solution. Neither of our original functions, log base 2 of x and log base 2 of x minus 1, neither of these two functions are defined for negative values. That means that this solution does not make sense. There's only one solution, and that is 1 plus the square root of 5 over 2. In our next video, we'll talk about how to do derivatives and integrals using these two new functions.